Imagine that we are experimenting in a field. We want to verify our belief that in this field, a particular flower species should occur approximately 3 times in a square meter. Due to physical restrictions, expense, and time, it is not possible to survey the field in its entirety. So, we must look at 3 smaller sites and use the information gathered from them to make a more general claim about the whole field. The experiment proceeds by checking each site and recording the positions of these flowers each time they are found. Before analysing this data, let's recap our assumptions and any important information. As stated before, we believe the occurrence rate is constant for the entire field. We also assume that the counts within each site are independent. The sites do not overlap, and we have no reason to believe that the count in one site depends on counts from other sites. Finally, we know that the total recording area of each site is different. So how do we use our data and assumptions to estimate a rate? One way is to use a Bayesian approach. The model is written mathematically like this. The tilde notation indicates that whatever is on the left has the distribution of whatever appears on the right. Lambda is a rate representing the number of flowers per square meter. It has a gamma distribution with a shape alpha and a rate beta. Counts recorded at each site have independent Poisson distributions. The mean of each Poisson is equal to the rate multiplied by an exposure term. The exposure describes how much observing we did. In this example, exposure is the area of each site. In Bayesian statistics, a gamma prior distribution and a Poisson likelihood form a conjugate model. This means that the posterior can be computed exactly. Before looking at this computation, let's review Bayes' rule and see how these components link together. Bayes' rule consists of 4 parts. The likelihood is a model for the data. It reflects how well the parameterized model explains the observed data. The prior distribution is where additional knowledge can be included. For example, from a previous experiment or measurement. The prior must not include information gleaned from the observations entering the likelihood. This can bias the posterior because the data will have been used twice. The posterior is a probability distribution for the parameters that combines information entering the model from the likelihood and the prior. It represents our updated belief about the parameters after observing new data. The evidence is a normalization constant that ensures the posterior is a proper probability distribution. When the number of parameters in the model is large, this quantity is difficult to compute. Fortunately, it does not change the shape of the posterior distribution, so it can be ignored. Working with the unnormalized posterior is common practice in modern Bayesian analysis. Let's look at the computation in more detail. The top line is the likelihood. Remember that the count recorded at each site is modeled as a draw from a Poisson distribution, with a mean equal to the rate lambda multiplied by an exposure term. The likelihood combines these independent counts by multiplying the distributions together. On the second line is the gamma prior distribution. Out the front of each equation are constants that do not depend on lambda and can be dropped. Following Bayes' rule, the likelihood is multiplied by the prior. At this stage, you might have noticed a pattern. Both the likelihood and the prior contain a power of lambda and the exponential function raised to a power that includes lambda. By collecting these terms together, we obtain something proportional to a gamma distribution. This highlights the conjugate part of the model. Conjugate models are not only simple to compute, but also highly interpretable, as we will see. Let's apply this computation to our running example. Remember, we are interested in estimating the rate of a species of flower at 3 independent sites within a larger field. To compute the likelihood, we need to organize the area and the number of observations made at each site into a table. Site 1 has an area of 8.25 meters squared, and 31 positive observations were made. In Site 2, 23 observations were made from an area of 7.5 meters squared. Site 3 is the smallest, with an area of 4 meters squared. In this site, a total of 12 observations were made. This information collects everything we need for the likelihood calculation. Next, we need to build the prior. The gamma prior distribution is defined by 2 parameters. a shape alpha and a rate beta. As the shape parameter increases, both the mean and variance of the gamma distribution also increase. In a conjugate setting, alpha can be interpreted as the prior number of observations. Conversely, as the rate parameter beta increases, the mean and variance of the gamma distribution decrease. Here, beta represents the exposure of our prior observations. Let's assume we visited a neighbouring field and observed 1 square metre of it, where we counted a total of 3 flowers. Since the fields are close to each other, we can reasonably assume that their environmental and ecological factors are similar. We can incorporate this measurement as prior information by setting alpha to 3 and beta to 1. This prior has a mean of 3, with a 95% highest density interval ranging from approximately 0.3 to 6.5. The highest density interval is the narrowest interval that contains a fixed percentage of the total probability density. It is useful for quantifying uncertainty in both prior and posterior distributions. We can now turn the handle on the Bayesian computation and see how our belief in plausible values of the rate changes as we observe each site. First, we start with the gamma prior. Then, we update our belief with information from the first site, the second site, and finally the third site. Each time we update, the uncertainty decreases and the posterior shifts closer to the true value. We can explain why this is happening by looking at how the posterior mean and variance change with the data. Since we know that the posterior distribution follows a gamma distribution, we can easily calculate its mean. This turns out to be the total number of counts, including those from the prior distribution, divided by the total area. As we observe more sites, the influence of the prior on this calculation diminishes. This makes sense. More information should convince us to change and update our beliefs accordingly. We can perform a similar analysis for the posterior variance. The variance of the gamma distribution is equal to the shape divided by the square of the rate. This suggests that the variance decreases as large areas are observed. This is also logical. The more observing that we do, the more certain we should be about the values our parameters should take. Bearing these in mind, let's look at the posterior update animation again. But what about if a conjugate model is not possible? In many real-world scenarios, such a model is indeed too simple. However, the concept of modeling a rate can be described by a generalized linear model. Again, we start with the Poisson likelihood with the same mean as before, equal to the rate multiplied by the exposure. Call this mu. The Poisson generalized linear model uses the log-link function to ensure the mean is positive. Our interest is not in directly modeling mu, but lambda. We can replace log lambda with a parameterized linear model of our choice. This video introduced a Bayesian model that combined a Poisson likelihood with a conjugate gamma prior distribution to model a rate from count data. To combine counts from different areas, the model must account for the size of these areas. This is possible by including an exposure term in the model. Exposure is not limited to just area. It can be any measurement that describes how much observing was done. For instance, in a different analysis, the exposure could be time. The gamma prior distribution is commonly used in Bayesian analysis. It serves as a conjugate prior for various models and is a flexible distribution for describing positive parameters. We examined how the shape and rate parameters of this distribution change its characteristics and their interpretations as counts and exposure. We also saw how a belief, represented as a prior, is updated in light of new data. As we observed each site, our belief about the rate changed significantly, transitioning from a broad prior distribution to a much narrower posterior distribution. When the posterior cannot be computed exactly, estimation is required. One common approach is to obtain samples from the posterior using Markov chain Monte Carlo methods. These samples can be used to visualize the posterior distribution and calculate its statistics, such as mean and variance. In the example presented in this video, we assumed that each site had the same underlying rate. While this assumption was appropriate for this fictional data, it may be difficult to justify in real-world scenarios. A common method for combining similar estimates is a technique known as partial pooling. This contrasts with models that assume all observations estimate the same quantity, complete pooling, or separate quantities, no pooling. The Bayesian approach is powerful because it helps us understand and quantify uncertainty. One of its most valuable applications is in making predictions. For instance, we could predict the number of flowers in unobserved sites using the posterior predictive distribution. Specifically, in our conjugate model, the posterior predictive distribution is the negative binomial distribution.